Okay, the last video that I want to do for this evening is on shapes of molecules. I didn't have a chance to cover this in lecture, but you could have some homework problems on it. And you really only have to know how to use a chart. So they call it Vesper Theory, which is valence shell electron pair repulsion. And what it means is valence electrons, like all electrons, hate each other, and they move to make three-dimensional shapes so that they can avoid one another. So if they can, they'll be linear. Like carbon, when it has two double bonds, the oxygens go on the complete opposite side, so the oxygens can avoid each other and these electrons can avoid each other. So it becomes linear. So if you have a central atom with no lone pairs and just two groups or just one group around it, it's linear. If you look at formaldehyde, so this is actually the preservative, and notice that the central atom is carbon still, but notice that the carbon only has three groups around it, and it doesn't have any lone pairs. They call that, I know the oxygen has lone pairs, but they only look at the central atom. The central atom doesn't have any lone pairs, and it only has three groups, so they will call that trigonal planar, and it literally looks like this. It's flat, and you divide a circle into three places, so you have 120 degree bonds. Remember that linear means 180 degree bonds, because it's a perfect line. The last key shape is when you have four groups around something, no lone pairs, then they call it tetrahedral. You would think that it would look like this, and you'd have 90 degrees apart, but actually, atoms are pretty smart. They know that they can bend and twist and get even further apart. So these two are straight in the plane of the paper. This one's coming out at you, and this one's going back, and they call this a tetrahedron, and it's the most stable form that four groups can have when you have no lone pair on the central. So no lone pair on the central atom, it's tetrahedral. And again, they're doing this because the hydrogens don't like each other. So even though the Lewis structure is fine, this is for methane, CH4, like this, the 3D structure or the Vesper structure will look like this. Sometimes you do have a lone pair, and lone pairs tend to push things down. Electrons actually, even though they're tiny, they take up all the space. So they'll call this where it pushes things down, and they want to talk about just where the atoms are. They call that molecular geometry. Not Vesper geometry, not electron geometry, which includes everything, but molecular geometry, which just looks at where the atoms are. And the molecular geometry is trigonal pyramidal, because that's literally what it looks like. It looks like a triangular pyramid with the lone pair pushing things down. Water, I told you the Lewis structure can be drawn like this, and it looks linear, but in reality, the lone pairs, and they should show all of them, are on the same side, and it pushes things down to give it a bent structure. Here's the chart that I was talking about. So you look at how many electron groups are around the central atom. They should say around the central atom. So here's the central atom, here's the central atom, here's the central atom, here's the central. It has to do with what everything's attached to. And when they say electron groups, they mean double bonds count as one electron group. Single bonds count as one electron group. Lone pairs count as one electron group, but you only look at the central atom when you're looking at electron groups. So this one has two electron groups. This one, formaldehyde, has 3 electron groups. This one, which is actually SO2, has 1, 2, 3, because you count the lone pair, electron groups. Methane has 1, 2, 3, 4 electron groups. Ammonia, NH3, has 1, 2, 3, 4, because you count the lone pair, electron groups. Water has 1, 2, 3, 4 electron groups. So notice that anything that has 4 electron groups is called tetrahedral for the electron geometry. This is the same thing as Vesper geometry. Things that have 3 electron groups around the central, and again you count the lone pair, are called trigonal planar for the electron shape, electron geometry, Vesper geometry, and things with 2 electron groups, or just one, if it's one bond like HF or Cl2, they are linear. And linear is easier, because if they ask the molecular geometry, which means where are the atoms with respect to each other, not the electron groups, it's also linear. So if you find that it's linear, molecular geometry is linear. But when you get lone pairs, the molecular geometry can change. So this particular essential atom, carbon, has no lone pairs, just bonds. So it's trigonal planar for the electron geometry and trigonal planar for the molecular. That means it literally looks like a flat triangle that's been cut. But as soon as you have a lone pair, the lone pair pushes things down, and now if you just look at the atoms, they're bent. Same with the 4. If there's no lone pair in the central, then the molecular geometry is tetrahedral. Notice the bond angles are 109.5, not 90, because it actually looks like this. But as soon as you get a lone pair, it pushes them down a little bit, and now it's trigonal planar. If you get 2 lone pairs, it pushes it down a lot more, and it's bent. And they say that the bond angle for these is like 109.5 for all, but actually every time you get a lone pair, it's a little less. This is probably 107. This is 104. This one without any lone pairs on the central atom is 120, but probably when it's bent and you have a lone pair in the central, it's probably like 118. Pushes it down by about 2 degrees. So you can use this chart to answer all of the questions on bond angles, electron geometry, molecular geometry. Just make sure that you're always looking at the central atom when you're answering these questions. If they ask about the electron geometry, you count the lone pairs as an electron group. Sometimes they'll call it an electron domain, same thing. And then when you do the molecular geometry, you also have to look at it. If it has 1 lone pair, it may be bent. If it has 1 lone pair and it has 4 groups around it total, including the lone pair, it may be trigonal pyramidal for the molecular. If it has 2 lone pairs but 4 groups total, it may be bent for the molecular geometry or molecular shape. They'll say molecular geometry or molecular shape. So just use this chart to help you. It's on slide 57. You can also look up electron and molecular geometries, and you can get a table of the shapes, but this is the easiest one to use.